Hello guys, welcome to the lecture 45 of deep learning series. In this video, we'll be discussing our final optimizer, that is Adam optimizer. Okay, this Adam optimizer is most widely used in all the deep learning projects. Okay, now in order to understand this Adam optimizer, I have divided this video into four parts. In the first part, we'll be discussing the prerequisites, and in the second part we'll be discussing the mathematical intuition of this Adam optimizer, and in the third part we'll be discussing the subtopic of this mathematical intuition, that is bias correction. Okay, and in the fourth part we'll be discussing the implementation of Adam optimizer. Okay, now let's start with the prerequisites. Okay, the prerequisites to understand this Adam optimizer is you need to watch my past four videos, that is the video on exponential weighted moving average and Nastro accelerated gradient and Adagrad optimizer and RMSProp optimizer. Okay, if you have successfully understood all these four topics, you can skip this prerequisites. Okay, and directly move on to mathematical intuition. For those who have not watched those videos, I'll be explaining about all these four optimizers in short. Okay, first let's start with batch gradient descent, stochastic gradient descent, and mini batch gradient descent. Okay, initially these were the optimizers that are used to train this deep learning models. Okay, now by using this optimizers, okay, like batch gradient descent, stochastic gradient descent, or mini batch gradient descent, basically people face the problem of slower training. Now, to solve this problem of slower training, next the optimizer, okay, the optimizer that came to solve this slower training is exponential weighted moving average. Okay, this exponential weighted moving average has successfully solved the problem of slower training. Okay, this exponential weighted moving average is basically entirely based on momentum. Okay, this exponential weighted moving average is entirely based on momentum. Okay, but due to this exponential weighted moving average, people face the problem of oscillations. Okay, due to this exponential weighted moving average, people face the problem of oscillations. Okay, now to overcome this problem, okay, to overcome the problem of oscillations, the optimizer that came is NAG. Okay, the snag means Nastro accelerated gradient. Okay, it basically solves the problem of oscillations. Okay, this basically solves the problem of oscillations. Okay, but both these optimizers are entirely based on momentum. Okay, both these optimizers, exponential weighted moving average and NAG, are entirely based on this momentum. Okay, now the next two optimizers, that is Adagrad and this RMSProp optimizer, are entirely based on decaying of learning rate. Okay, they are basically introduced to solve the problem of elongated bowl. Okay, elongated bowl problem due to sparse data set. Okay, now after this we have discussed Adagrad optimizer, which solves the problem of elongated vowel problem. Okay, but the problem with this Adagrad optimizer is it doesn't converge to the global minima. Okay, after how many epochs, okay, after how many epochs you train, it doesn't converge to the point of global minima. Okay, it doesn't converge to global minimum. Okay, now to solve this problem, okay, to solve this problem, the next optimizer that came is RMSprop. Solved problem of convergence. Okay, this RMSprop optimizer has solved the problem of convergence. Okay, now these are the four optimizers that we have discussed earlier. Okay, these two optimizers are based on decaying of learning rate. Decaying of learning rate. Okay, now this Adam optimizer is a combination of all these four optimizers. Okay, let's see how. Okay, this Adam optimizer combines the concept of momentum and decaying of learning rate. Okay, the concept of momentum and decaying of learning rate combinedly introduces Adam optimizer. Okay, concept of momentum plus decaying of learning rate gives us Adam optimizer. Okay, now when you move on to this mathematical intuition of this Adam optimizer, you'll be understanding this statement in detail. Okay, now in the next section of the video we'll be seeing the mathematical intuition of Adam optimizer. Let us now discuss the mathematical intuition behind this Adam optimizer. Okay, over here you can see that these three equations, okay, these three equations are the mathematics of this Adam optimizer. Okay, now let's decode these three equations in our style. Okay, first this wt plus 1. Okay, this wt plus 1 is nothing but our next upcoming weight. Okay, at epoch 1 if we have this weight, at epoch 2 we are calculating this weight. Okay, that is w2. Okay, wt plus 1 is equal to wt minus learning rate divided by under root v cap of t. Okay, v cap of t plus epsilon into m cap of t. Okay, now here if you observe this first equation in you can see that this part, okay, this term, okay, this term represents learning rate decay. Okay, in our equation this part represents learning rate decay. Okay, now after this part, okay, that is m cap of t represents the momentum. Okay, in our formula this term represents learning rate decay and this m cap of t represents the concept of momentum. Okay, now let us see where do we actually calculate this v cap of t and m cap of t. Okay, first mt. Okay, first when it comes to mt, this is nothing but the momentum. This equation is responsible for applying the momentum in our Adam optimizer. Okay, this mt is equal to beta 1 mt minus 1 plus 1 minus beta delta wt. Okay, this term represents exponential weighted moving average of our past few gradients. Okay, this term represents exponential weighted moving average of our past few gradients. Okay, here this beta 1 and beta 2, okay, over here beta 1 and beta 2 are nothing but decaying factors. Decaying factors. Okay, this entire term represents the concept of momentum. Okay, now this vt is responsible for applying the learning rate decay. Okay, vt is equal to beta 2 vt minus 1 plus 1 minus beta 2 delta wt whole square. Okay, now here this beta 2 is nothing but decaying factor. Okay, this beta 1 and beta 2 are nothing but are decaying factors. Okay, now here we calculate mt and put it over here and vt and put it over here. Okay, so in this way we apply the concept of momentum and learning rate decay in our Adam optimizer formula. Okay, now you may have a doubt that what are actually this values of t and what are the actual values of this beta 1 and beta 2. Okay, now this t represents epoch number or iteration number. If you are proceeding with mini batches, okay, if you are dividing this whole data set into mini batches, then this t represents the iteration number. And if you are going if you are considering the whole data set as a single batch, then this t represents the epoch number. Okay, this is the value of t. Now this beta 1 is equal to, okay, most frequently used beta 1 value is 0.9 and the most frequently used beta 2 value is 0.9. Okay, most frequently used beta 1 value is 0.9 and beta 2 value is 0.9. Okay, now here this mt is responsible for direction of the gradients. direction of the gradients. Now if we assume this as our graph and this as our global minima point, this direction, okay, whether it must move towards this global minima point or opposite to the global minima point, okay, this is represented by this empty. Okay, this empty is responsible for the entire direction of our optimizer. Okay, in which direction we must move, okay, in which direction we must update the weight, that is taken responsible by empty term, and this vt represents the magnitude of direction, sorry, magnitude of gradient. Now, on how much pace the update must be taken. Now, let's say this is a graph and the amount of jump, okay, the amount of jump taken by the optimizer is directed by this VT term. Now, it may take a smaller jump and larger jump based on this VT value. Okay, this VT value is responsible for the magnitude of jump. Okay, it is responsible for the magnitude of jump. Whether our optimizer may take longer jump or whether it may take shorter jump, it is directed by this VT term. Okay, empty term represents the direction and VT term represents the magnitude of the jump. Okay, magnitude of the jump. Okay, now here you may have a doubt that in this formula we have actually used v cap of t. Okay, v cap of t and m cap of t, but why are we calculating this mt and vt? Okay, now this term, okay, this empty term and vt term are calculated and then applied bias correction. Okay, this first what we do is we calculate this empty and vt terms. Okay, now after calculating this empty and vt terms we apply bias correction. Okay, now after applying the bias correction, the final outputs we get, okay, the final outputs we get are m cap of t and v cap of t. Okay, now we substitute this m cap of t and v cap of t in this formula. Okay, this is how Adam optimizer works. Okay, now let us see the concept of bias correction. Why do we actually do this bias correction? Now let's say let's assume that we are training at our first epoch. Okay, let's say we are training at our first epoch. Now at the first epoch training, what do you think might be the value of this mt minus 1, that is exponential weighted moving average of past gradients? Okay, at the first epoch we don't have any average of past gradients, right? Okay, at the very first epoch we don't have the exponential weighted moving average of past gradients, so obviously this value will be 0 and this value also will be 0 at the very first epoch. Okay, now when these values of when these values are 0, then the updates are very small, right? And when these values are 0, the updates are very small. Okay, now in the initial stages of the training, any optimizer, okay, if you any optimizer we use, we need the update, we expect that it must take longer jumps. Okay, then initial stages of the training we expect a longer jump from any optimizer, but when these values are 0 at the initial stages of the training, what happens is this Adam optimizer takes smaller jumps. Okay, due to this values becoming 0, okay, due to this values becoming 0, our Adam optimizer at the initial stages of the training takes very smaller jumps. That is, the updates will be very much negligible. Okay, there will be no much difference between wt plus 1 and wt. Okay, there will be no much difference between wt plus 1 and wt. So to solve this problem, okay, to solve this problem we introduce bias correction. Okay, now we apply bias correction by this formula. Okay, first we calculate mt and vt, on this we apply bias correction, that is m cap of t is equal to mt divided by 1 minus beta 1 t, and v cap of t is equal to vt divided by 1 minus beta 2 of t. Okay, here t represents same epoch number or iteration number, and this mt is from here and this vt is from here, and beta 1 and beta 2 are our decaying factors. Okay, this is basically what this formula represents. Now to understand, okay, to understand we need to see an example. Now to understand this, let us initially take few assumptions. Okay, let's say beta 1 is equal to 0.9. Okay, I'm explaining this example only with respect to empty, and same goes with VT as well. So that is why I am explaining only with respect to empty term. Okay, now beta 1 is equal to 0.9, and let's say t is equal to 1 at the first epoch of training, and empty minus 1 will be obviously 0, and let's assume that delta wt is equal to 1. Okay, now let us substitute all these values in this formula. Now the empty value would be 0.9 into 0 plus 1 minus 0.9 into 1. So this comes out to be, this entire term will be 0. 1 minus 0.9 is 0.1 into 1 is 1. Okay, this is the value of empty. Okay, now this empty is 0.1. Now if we directly substitute this 0.1 in this formula, what happens? See, this entire term will be obviously smaller as we are applying learning rate decay. The initial stage will be having some smaller learning rate, that is 0.1 or 0.01. Okay, now when I multiply this with 0.1, okay, when I multiply this 0.1 or 0.01 with this 0.1, then the entire term would be definitely a smaller term. Okay, the combination of both this will be definitely a smaller term. Now when I subtract this smaller term from this wt, this wt plus 1 and wt will be nearly equal. Okay, wt plus 1 and wt will be definitely nearly equal as I'm subtracting some smaller value from it. Okay, so to avoid this, what we do is we apply bias correction. That is, how do we apply is m cap of t is equal to, we have already got our empty value, and 1 minus beta 1 value is 0.9. so this comes out to be 0.9 divided by 0.1 divided by 0.1, and this comes out to be 1. Okay, so when I substitute this m cap of t over here, you can see that 1 into some 0.1. so definitely there will be a change between wt and wt plus 1. Okay, previously if you see, this is 0.1, and now if you see, it is 1. so there is a major difference. Okay, there is very major difference between 0.1 and 1, right? Okay, so when you substitute this 1 over here, we can see we can definitely see a change between wt plus 1 and wt instead of using this 0.1. Okay, this is the entire concept of bias correction. Okay, so to avoid the slower training at the initial stages, we use this concept of bias correction. Okay, this is the entire mathematics behind Adam optimizer. In the next section, we'll be applying this Adam optimizer on a sparse dataset. Okay,
let us implement our Adam optimizer on a sparse dataset. First, I am importing the basic necessary libraries, and then I am generating my sparse dataset. Okay, this code generates basically my sparse dataset, and here I am doing model building, and here I am implementing my Adam optimizer. Okay, optim.adam. Okay, optimizer is equal to optim.adam basically implements the Adam optimizer in our model. Okay, now in this Adam optimizer, I basically have few hyperparameters. First, I am initializing my model parameters, then I am using learning rate as 0.01. Okay, this is my initial learning rate, but at the further epochs of training, this learning rate gets decayed. Okay, now this beta 1 beta 2 values I am initializing to 0.9 and 0.999. Okay, it can be also 0.99 as well, and epsilon value is equal to 1 e minus 8. Okay, this epsilon value is basically some smaller value, and weight decay is obviously 0. As I am working on regression problem, I am using mean squared error loss function, and I am training it for 100 epochs. You can see that after 100 epochs of training, I got loss as 0.9683. Okay, this is how basically you implement Adam optimizer in your code. Okay, by using optim.adam. Okay, by using optim.adam, you implement Adam optimizer in your project. Okay, hope you guys like this video. If you like the video, please like, share and subscribe. Thank you.